With this summer school, it has been running for a very long time. So you get introduced to Gaussian processes, which is nice. And now I'm going to give this talk where I'm going to restate a lot of the things that Rich said. I'm going to confuse you by saying them in a different way. Hopefully, some of this together will get into a space where we can all figure out what these things are. But except for other things, Gaussian processes relies on a certain set of rules. So I thought I was going to start talking about the motivation, why we're using Gaussian processes, and why it's a sensible thing from a bit of a bigger perspective to begin with. Another thing is that there's kind of a nice thing that if you come here, there's quite a good chance that in a couple of years' time, you might come here and give one of these talks. So we're a bit of a club. And one of the things that this club is doing, as well as doing Gaussian processes, is following the rules of cycling. So I'm not sure if you're familiar with the Illuminati. They are the ones to set up the rules of cycling. And one of the important rules of cycling is, and we'll see how this goes this year, is that tan lines should be cultivated and kept razor sharp. That's why I look like this. You've got a few others here in the audience as well, and hopefully after having got into Gaussian processes, you'll also follow the rules of cycling. So I'm going to continue talking about bikes. So I used to give this intro, and then I had this bike that I was showing, which was a Colnago Master Extra Light Art Deco Campagnolo Super Record, and I said, this is my dream bike, but I'm an academic, so I'm never going to be able to own this. However, this summer, I managed to get hold of one. This is from 1998, taken in my hometown, so I actually own this bike now. It's the nicest bike you could ever ride. So, I used to live in a previous life over in Bristol, and in Bristol you can do a lot of good cycling. So one path you can go north, you can go to a place called Port Talbot in Wales. Port Talbot has a big port and there's a steelworks there. Steelworkers eat a lot, cyclists do as well, so you go there and eat at their cafes. Another route you can go is you can go south and you can get to some nice hilly places in Exmoor. And at one time, I was at this place here in Lynmouth. And I had a look across the Bristol Strait, and I took this photo. And I saw this, and I was like, okay, cool. There's some buildings there. That's clearly the steelworks in Port Talbot. So then I cycled home. It's about 150k, so I had a lot of time to think. So I was thinking, why could I actually see this thing? So I came home, took a measurement across the channel, and then went into this simple calculation and thought that if the Earth has a specific curvature, the distance to the horizon at the point where I was 6.2 kilometers. At the distance between Lynmouth and Port Talbot, the hidden height behind the horizon should be 125.6 meters. So then I had a look at this photo again, and you can see there's some big chimneys there. You can go to tallbuildings.org, and you can figure out how tall they are. And you realize they're a hell of a lot shorter than 125.6 meters. So then, of course, you start questioning things, right? And now I'm a machine learner, right? So I got data. So I need to fit my model to this data. And then it became, obviously clear to me. So I ended up cycling back home and having this clear now conviction that the Earth is flat, right? And it's really great that you laughed. If you wouldn't have laughed, we would have had to change this lecture because we would have had some other issues to deal with before we get on to Gaussian processes. But the reason why I wanted to talk about this was that basically what we have is that we've got two explanations of why this phenomena, why this data could be explained, right? We have the first one, which is just, well, the Earth is flat, so the water surface is flat, therefore I can see the building, the end. It's really simple. Then you have another explanation, which is Due to the temperature gradient between the water and the air, there's a dispersion of water molecules into the air proportional to the distance to the surface, effectively creating a lens, allowing us to see around the bend, right? Now, some people will say, well, you know, if you've got two equal explanations, you should come up with the notion of Occam's razor, right, that we pick the simplest one. Well, let's pick a measure of simplicity, and we can say the first one has a lot less letters in it, right? So it isn't just easy to do this. Now, what we're going to talk about is fitting curves, right? So now let's take exactly what we talked about, but just take it to this concept instead, right? So you've been given a set of data points, and our notion now is that we want to fit a curve to it so that we can reason about points where we don't have any data, right? This is the funny thing, right? Training data, the data I have, is the only points I do not care where the function is, right? Because I'm never going to ask that question. I only care where I don't have data, right? So what we can do is the most likely, we think something like that would be nice. We've seen things like this. But actually, all of these are under the data completely equivalent, right? They all explain the data exactly the same, but they're all very different between the data points, right? And what we want is some form of notion, this is all of machine learning effectively, that helps us separate these two. Okay, so there's really two components, and we'll come back to this funny Pareto front graph later on. There's really two components to any machine learning system. You've got data on one hand, and you've got knowledge on the other hand. The reason why I draw this like this, and hopefully this will be clear eventually, is that you have a couple of different settings. On this line here is the different ways you can solve a problem. You can be out here, where you've effectively seen all the data that you're ever going to see. You're going to see a data point at every question that you're going to see. This is not machine learning. This is a lookup table, right? Got the other end of the axis, where I've seen no data whatsoever. Now I need to know the mathematical form of the function to be able to say anything, right? I need complete knowledge. And then machine learning, that's not really machine learning either, right? Machine learning is the thing that sits in between, where I have a bit of data and I have a bit of knowledge, and the aim is to put these two together to find something, right? I don't have completeness of anything, right? And that's what we're going to do on the bigger picture, and we're going to show why Gaussian processes are a really cool way of doing exactly this. So, I usually say machine learning is the task of combining integrating knowledge with observations to perform predictions using the subset of possible explanations that are consistent with both my knowledge and my observations. Now, someone can say, is Rich still in the room? No. Then we can make fun of statisticians. So isn't this statistics just then? Well, it is. This is exactly, machine learning is nothing but statistics, except for we have a slightly different narrative to what we do. Statisticians usually care about parameters of the knowledge. However, what we really care about, in most cases, is how we use these parameters to do predictions. And this slight change of narrative has enabled us to do quite cool things, also quite scary things, because if you don't care about the parameters, you don't really know what you're doing, and that can be scary sometimes. Great. So, to formalize this a little bit, to see the components of what we need in any machine learning system, and then to see how GPs fit into this, let's start just setting up what machine learning actually is then. So we got a domain set, which is a set of measurements that we somehow want to label. If we think about a classification, it's a discrete label, it's a continuous. And then we got a set of outputs, so these are the effective labels that we have. So I'm calling that Y. So we now have a finite sequence of pairs, X and Y, which is our training data. And then this training data, this data that we're looking at, is not just, it follows some form of structure. So it follows some underlying probability distribution D that governs these measurements. And then we have some form of data generation process. So the process that takes our input to our output. So I'm calling that F. And then what we want to do is that we want to find a prediction rule that says H, which is trying to recover F, right? And this is the object that encodes the knowledge that we try to recover from this data. Okay, so we can take this as an example. This actually is a visualization that actually shows you all of the components that we had before. So we have an input domain, which is this plane. We have an output domain, which is just one dimension in this case, so that will be the color that's red or blue. Got a data distribution, which is these two Gaussians, and then I have a generating thing that is this, right? Which is just this dashed line, right? So that's F that just tells me which side of each one am I here. Cool? So in order then to learn something from this, I need some form of measurement of success. So that I can say, if you come with the Earth is flat and I come with it's spherical, I can plug these in and then we can say how well they do. So I need some form of measure of success, right? So the best thing we can think about, right, would be something like this, right? Where I take the probability of all the points that are effectively misclassified if we think about classification here, right? So everything where H is different from F, and I get a higher value of badness if it's a point which is very probable, right? Okay? Cool? So that's what's called the true risk of any model. Now the problem with that is we do not have access to D. If I have the true data distribution, well, I don't need to do all of this learning stuff, right? I know how the data is distributed. I don't have that, so I can't actually compute this thing. So I neither clearly have access to F. Because if I have F, just F is equal to H, job done, right? So that's a bit of a problem, right? So what we do instead, right, is that this is what we have, right? I don't know how probable the blue or the red ones are, right? I don't actually know where this boundary goes, so I can't compute this thing called the true risk. So what we do instead is that we do something then called empirical risk minimization, where we take an empirical measurement of this thing called the true risk, right? So what I say here is that I assume first that the training data S that I've been given is a good sample, is reflective of the distribution as a whole, right? If it's not, I've been given very off data, and it's a hard thing to do. So I assume that. And then what I do is that I effectively say, I make the assumption that each data point is equally important. And then I just count up the things that are misclassified, and I take an average of that, right? That's effectively my empirical measure of risk. So now, if I would then want to try this H, how do I find this H, right? So here is a measure. If you give me an H, I can say how well it does on the training data, right? That's fine. But how do I get the H, right? That's the big thing, right? So to get the H, we normally use some form of algorithm, right? We design some form of algorithm that searches for H. So that normally takes the data as an input. So I have some form of, this is very abstract, right? But we're used to putting the key points on learning. So I take some form of algorithm, I chuck in my data, and then it spits out a hypothesis, okay? Then, if this algorithm takes in some data and spits out a hypothesis, it needs to work in some space, right? It can't just like give you any hypothesis, right? You have to have a finite set or some set of hypotheses that it can look for, right? So let's think about this, right? Let's say you want to fit a line and it's a polynomial, it has this specific degree. Now you have a set of parameters. This means you design an algorithm that walks around in this space, right? Cool. So we have a finite set of hypotheses, capital H, which we're trying to find this is. This is effectively choosing the type of models that we want to fit. So if I would do this, if I would apply this, I would take this algorithm in this hypothesis space I would have, and I would apply this, I would run this, and I would get something out. There's 4 things that can happen. So here I'm trying to sketch a visualization of the error that I can have. So H star out there is the optimal thing. That's the thing that I'm actually looking for. We could call that F if you want to. Now, I have parameterized this space of hypotheses. That's this red thing, right? So it doesn't actually contain the true solution, the one I'm looking for. It's outside. Then I have H opt. That's the optimal hypothesis inside the hypothesis space that I've chosen. Okay? Then I have H hat opt. This is the optimal hypothesis on S. It's the best thing I can do on the training data. So if my algorithm is in some sense perfect, I will find that. Okay? And then I have H hat, which is the hypothesis that I actually found. Right? So now if we break this down, if we think about the difference between these errors that I have, we can do it like this. So the difference, if we start from the top, the last arrow there effectively says the difference, the error that I will have always get by choosing the wrong model class to work with. Okay? So let's say this circle, I decided I'm just going to look at lines. And it turns out it's a quadratic function, right? Then that error is the thing that I'm going to get from this. Okay? That's the last error. Then the error between H hat opt and the H opt is the thing that I get by having a badly sampled data set. Right? So that's the difference of saying the best thing I could possibly do in this class, if I knew D, if I knew the true distribution of the data, to the error that I will get because I have this finite sample set. Okay? And then the final thing is the difference between what I end up getting to what will be the best thing on that subset of the data in this hypothesis space. So that's the thing induced by picking the wrong algorithm, right? So now you have these 3 components which we really have to think about picking. Now, it's first the algorithm. Oh, let's start from the outside. It's first, what model should I use? Then it's having the correct data set, and then it's picking the right algorithm, right? These are the 3 things we always deal with when we do machine learning. So, cool. Let's think about how they work then. So, this is going to be trying to motivate why we're using Gaussian processes in this case. So, what does the algorithm actually do? Actually, a lot of the work on things like deep neural networks and so forth is actually on the search problem itself. Because you can think about the algorithm as a search. You're dumping this thing into a parameter space, and then you're walking around trying to find some form of solution to this. Now, we want to bias this solution because we want, exactly as we saw before, we want the solution that we like. In the case of me fitting that sine curve, I want that nice sine curve, not these ones, right? So how do you do that? Well, you can say, well, actually, all these solutions that are very high frequent are down this end. So I put on an eye patch there, so now my algorithm can't see them. And then I might say, well, actually, turns out in this error landscape, and this is very true for neural networks, there's solutions which are like bad, 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 super nice, bad, 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 right? You change a parameter a tiny bit, and it gets really good. We don't like them. So what do? We put clown shoes on our algorithm, so it can't fall into those, right? So it walks around this, right? This is what a lot of the tricks of learning neural networks actually does. It puts biases, knowledge, if you want, into these, okay? Then you have the next thing, which is saying, well, I can put bias and knowledge into the data set that I have itself. So, for example, I want to learn to classify my mum separate from my mum's dog, right? So now I have images of that, but it turns out my mum's still my mum if I turn her upside down, right? So what I do, I take all images of my mum and I rotate them, right? Cool. That's data augmentation, classical way as well of doing this. Can get really expensive and can get really hard because these symmetries, except for with my mum, they're kind of often very hard to think about, right? And then you have the final thing, which is the thing that we're really going to talk about. So hopefully you kind of gotten that I made fun of these two first parts. Now I'm going to stop making fun. So that is how we choose our hypothesis space. How we think of structuring the hypothesis space itself to say, these are solutions that I like, and these are solutions that I don't like, right? So putting a measure that reflects our knowledge directly on edge. Cool. So now, in order to do that, we are not going to do things like, let's say it's only lines, let's say it's only polynomials. That's too hard of a choice. So what we're going to do is we're going to put a continuous measure on these. We're going to put a probability distribution, which you should just think about as a measure of goodness. This I really like, high probability. This I really don't like, low probability. So we're going to think about how we can put probabilities on the hypothesis space of functions itself. Cool. So used to then do the bit of a Bayesian spiel on this to show how are we actually doing this and how does this mechanism work in the Bayesian setting. We've all seen Bayes' rule tons of times. The only thing Bayes' rule is doing is that it takes a prior measure, so theta here is my parameters to somehow represent some data. It takes a prior measure, the measure that I think, before I've seen any data, I think this is good and this is bad. It updates that to a posterior measure, which says, now when I've seen this data, and you thought this beforehand, this is the new measure, right? That's the only thing it does. So if you remember my graph, it's exactly the thing that takes that axis and this axis and combines them. So that, in effect, is machine learning if you want to. Now, the interesting thing that does this is the denominator of this thing, the P of D, the marginal likelihood. That marginal likelihood, we all know we get from integration. Now, if anyone studied measure theory here, you'll laugh at me. I just have this hobby intuition of what marginalization is that I wanted to convey to you. So let's look at this. We've seen this so many times, and let's just reflect over what this is. Okay? So we have a likelihood that effectively says, if this is the parameter setting now, this is how the data should look like. Cool. That's the model that generates data from parameters. And then we have this bit, p theta, d theta. Okay? D theta here is the canonical measure of the theta space. It effectively just taken theta and sliced it up in equal parts that are infinitely small, and then we just sum over each of them, right? But now we multiply that with p theta. So another way of thinking about this is thinking about this as a new measure. So we think about this as dt of theta. It's a measure that reflects my knowledge about theta. I'll try and show this in a graph. So let's say, sorry that it says x and y here. X should be theta in this case. Okay? When I compute my initial integral, I say this here is the parameter space theta that I'm reasoning about. Cool. Now, you've given me some knowledge that says, you know what, parameters here I like, parameters here I like, and parameters here I don't like. What happens when we integrate, you can think of from the cumulative distribution of this. So this is what I'm actually doing, a transformation of variables. If you look at the blue line, on that axis now you have dt theta. What has happened with this region here that I don't think makes any sense at all? Well, it has no space in the new axis, right? No space at all. This region here, where I got a lot of probability mass, whoop, it takes up a huge part of the y-axis, right? So the only thing you're doing when you're marginalizing is you're reparametrizing a variable to reflect your belief. And I just think that's a very simple way of thinking about it in terms of space. Initially, I had all these variables, right? I had from here to here, and then I say, you know, I don't like these, so I'm going to compress them. These I like, I'm going to make them really big. And then, when you apply your algorithm to this is a hell of a lot easier to find. That's effectively how Bayesian machine learning looks like. Okay? Cool. Another way that you often see this shown as instead is as distributions like this, right? So in this case, I have a likelihood function here where I say I have a line and it's plus minus something. I have different priors, different beliefs over what I think the slope of this line is. If you integrate them out, it looks like this, right? So the red one at a very concentrated belief means very few parameters. What I could do, if I wanted to do my space thing instead, is to make sure that that space was transformed so that it was uniformly red everywhere. It would, you just compressed all the other lines. Okay? Cool. So, what I'm going to do is I'm going to skip this. I'm going to stop this here. So, basically, the way I think about this is that the Bayesian argument implies that you try to reparameterize the hypothesis space to reflect your beliefs. A good analogy, which I think, hopefully you got it, is to think about space, or like what it occupies in the new parameter space. The believable parameters get more spaced, and the parameters that I don't like get less space, right? That is going to help my search, because all the things I believe a lot in are going to have more volume, effectively. Now, so what is then a good parameterization? So I've said this thing that hopefully we agree. We've got the algorithm, we've got the data, and we've got the hypothesis space. What we're going to talk about is the hypothesis space. And I said, I want a parameterization of the hypothesis space that allows me to do this work. So what do I want from a good parameterization? Well, I want something that's flexible in the way that the stuff I know I can easily put in, right? So that it encapsulates the things that I do want. I don't want to make a trade-off that says, I really want this, but I can't actually formulate that, so I'll do this, right? So I want it to be flexible in that way. The other thing is that I want it to be narrow. And what I mean by narrow is that I want to make as firm beliefs as possible onto something. Remember this thing that I showed here? The more knowledge you have, the less data you need, right? We always want to use as little data as possible. So the whole notion of finding an algorithm or a method that just works for everything is not true. What you want is something that works for as few things as humanly possible, including the thing that you want, right? That's the thing you're looking for. So you want something that can be flexible, that includes what you do, but when you decide what to do, you should be able to squeeze it down. Okay? And ideally, I want to come up with something that's interpretable, such that I can go to a domain expert that knows something about a problem, and they say, molecules work in this and this way. And I can say, aha, perfect. And I'll write down what that means. Right? That's what I want. Cool. So now we're then going to go to the GP introduction. and I'm going to try and convince you that Gaussian processes fits kind of this narrative. But before that, do we have any questions on the first part? No questions. No one believes the Earth is flat? No? Okay, good. We don't want that. Cool. So then I'll continue. So what I'll try to do first is that I'm going to explain very briefly what non-parametrics are in a general setting, and then we're going to see how we can define non-parametric functions. Okay? Great. So, this is our problem. We want to be able to find a measure over this space so that you can a priori say the magenta and the yellow, or the orange, or whatever horrible color I chose, are things I don't like. That's effectively what you want to say. Or you might want to say, I really like magenta, but I don't like the other two. Right? Dependent on your problem. So, we're going to use that again through a rule of cycling. So, rule 47 is drink triplets, don't ride triplets. That is, you don't have 3 cogs in the front, but you should drink Belgian beer. Okay? So, I'm going to use the example of beer. So, I like beer a lot. And now, hopefully, I'm going to have a beer with Søren and Maurizio and others during this, and all of you actually, during this event. So now it turns out I need to explain to one of you the fantastic beer I had yesterday. Okay? So there's 2 ways of explaining this, right? Either what I can do is I can say, cool, you know what, I found this amazing beer, so I went to the brewery's website. I actually had to hack their website to find their recipes, but here's the recipe. And now maybe one of you are brewers who will be like, wow, that's amazing, let's go and drink that. But I bet you for most of us, it doesn't make any sense at all, right? So another way of saying is, thankfully I'm among friends here. So what I can say, you know, Henry, the beer I had last night, it was a little bit like that bitter we had in Sheffield at the body, but then the head was kind of like that fruity IPA we had in Copenhagen, right? And he would be, oh yeah, I like that, right? So I give an explanation of something by relating it to other things. This is what we call a non-parametric explanation, right? While the first thing is a parametric explanation. So now, let's think of examples of this and why this is good. So let's say we got this black dot sitting empty in this space. Now, I want to somehow explain this thing. Well, it's kind of hard to explain this thing, but I see more dots. So now I see another dot. If I want to give a non-parametric explanation of this, I can relate that dot to this dot, right? So the simplest thing would be a nearest neighbor. I would just say the black... Okay, well, so the black dot is the red dot. I will just take all the characteristics of the red dot and make it the black, right? So the first beer you had tasted terrible, so now you have another one, you say, well, the black dot's going to be terrible as well, right? The end. However, and now this analogy goes a bit funny, the more beer you have, your capacity for explaining stuff is going to get a better and higher granularity. Not if you have them all in the same evening, but except for that. So now, the granularity of your explanation will become better and better. And this is, you might have heard this, the non-parametric models have infinite capacity. This is exactly an evidence of this. The more stuff you see, the better your explanation becomes, right? Okay? Now, in this case, a nearest neighbor, the only thing I did was related to say, black dot is the same as the closest red dot, the end, right? Super simple. Now, what you could do is you can also say something like this. Well, I'm going to tell you by some measure, again, of how the black dot relates to every other thing. Here I've just taken the Euclidean distance and I did some coloring of the blue lines to show how much similar they are. So maybe I can weigh them together in some cool way, right? Or I can do something like this, where I say, okay, they're all related through a shortest path, for example. This is just a different type of measure that I put on this space. But it all has the same characteristics. So what we've moved now is from an absolute measure of the parametric model, how much yeast, how much barley, to saying, a relative measure, if I come up with this one has more barley than this one, and reasoning like that. That's being non-parametric, and now we've basically put one challenge, the absolute parameterization, to the relative parameterization. And we'll see that that is quite beneficial. Cool. So let's talk about non-parametric models then, and specifically about functions. Now, this will be a massive overlap to Rich, so please stop me and ask questions now if I say things that he says differently and so forth. So what we want is we want to come up with a measure over this space, over the space of functions. Okay? That's kind of hard. I don't even know what a function is, really. Well, one thing I know, so let's like dissect down what a function is. If I draw a line at 3 from minus infinity to plus infinity, what do we know about minus 3? We know that the function passes this line once and only once. If it doesn't pass, well, the function is not defined there. If it passes more than once, well, it's not a function, right? So we know something there. Cool? So how about we then say we're going to parameterize our belief over where we think the function intersects that line. Now, we're going to say that that is a Gaussian. And this is actually very nice with this max entropy property here, right? We're effectively saying that I believe, this is my belief over where the y value is at x equals to 3. And I've just parameterized this with the Gaussian, the end. Okay? Now, I can do the same thing at minus 2. Now I've got 2 of them, right? So now we've got 2 function values that I've parameterized. And so effectively, I got Gaussian function values. I have 2, the red and the green, which has a mean and a variance. Boom. That I can now parameterize. Okay? Still not very interesting. Now, the next more useful thing that we think of functions is that if I would know the function value at minus 2, you probably think that that's somehow informative of the value at 3, right? Because functions tend to correlate across. Otherwise, it's white noise, right? If all the function values are independent, it's not really any interesting function, right? So now, let's say I know the value at minus 2 to be 2. Let's actually say that I'm a little bit uncertain of it. So I say it's a Gaussian, but it's a very, very narrow Gaussian because you told me the value, and I have just met you, so I don't really believe you completely. So it's a tiny bit of variance, right? Now, the question we want to answer then, what does knowing that tell me about this? Well, either we can say it tells me nothing, so it's exactly the assumption that I had initially. It's the same Gaussian. Or it tells me everything. So it actually says that if I know it there, it's just the same thing. So it tells me. Or it's somewhere in between. Right? Now, if I could parameterize this characteristic, this would be a really useful way of parameterizing a function. Right? If I could parameterize this for any x value. So then, let's just look and say that if this is true, then we don't have 2 function values that are just independent, 2 Gaussian function values. We got a 2-dimensional distribution of function values. And we still have those variances that we picked previously. Now the question is, what are the covariances? Well, the covariants are the thing that parameterize exactly that transfer of information, how much one slice covaries with the other slice. So if we just look very quickly on the conditional distribution of some Gaussians, right? So at the bottom here, I got the function value, so the y value at, let's say, the red slice, On the y-axis, I have the function value at the green slice. If this is my covariance, we can see that the conditional distribution, if I believe that the red slice is -1 or the green slice is -1, then I think the red slice has now been shifted down from its prior because information flows between them. If I pick the case where the covariance is really high, then an enormous amount of variance flows between them, right? And if I say it's 0, then all these conditional distributions are exactly the same, right? So, if I can parameterize the covariance between these slices, I get exactly the behavior that I was looking for. So, let's do that. Let's just take these two slices. There's no Gaussian processes yet. And then I say, I'm going to take this two-dimensional Gaussian, and I'm going to draw a sample from it. This here is the green slice. So I go in there and I take like -1.8. So the intersection at the green is 1.8, and at the red one, it's around 0. And then I draw a line between them. I can draw a couple of more samples from this, and I get this, right? I get these lines that wiggle dependent on how much variation I share between them. So now if I take a higher covariance, such that looks like this, now they don't wiggle particularly a lot at all, right? Because now they covary massively, right? And if I take a spherical one, now they are not independent because they all have a variance term. They are independent, but the scale is not. So, but you can see that they now vary a bit more than in the 0.5 case, right? Cool. Okay, let's start building this up to a Gaussian process. Cool, so I made two slices on this real line. Well, there's nothing saying that I can't make 3, that I can't make 4, that I can't make tons of them. Actually, how many slices can I draw off the real line? Well, infinitely many, right? So I can draw infinitely many slices here. So let's say that we take n slices instead. Now, that leads me to this n-dimensional Gaussian. So each sample from this will be n-dimensional. In our two-dimensional case, each sample was two-dimensional. Now it's n. So now comes a really cool property of the Gaussian, which is a bit, well, which is really funky, that helps us to do math a lot easier. Rich talked a little bit about Kolmogorov's extension theorem, but this is one of the key things that allows us to lift the distribution to the infinite case. So, say if you have this two-dimensional Gaussian distribution, and now I want to compute the marginal distribution over x1. I would just want to see how does x1 vary. Well, we do that by integrating. If you integrate that, you get this thing out. Yeah? That's the marginal property. Now comes the marginal property. If I instead take a really big Gaussian and I integrate, well, exactly the same thing happens, right? So the only thing you need to do to get the marginal distribution of one variable is to pick out its mean and its covariance element. I can give you, I'll show you that later, but I have a worksheet that computes all these, does all the math for all the Gaussian identities. I never did them when I was a student, and then I got scared when I started teaching that someone would ask me how to do the math, so I had to do it. And now no one asks for them. But I'll share that with later. But you can see here, right? The marginal distribution is the same. And now let's just make a leap of faith here. So if I then, how big can I make this thing? Well, I can make it infinitely big. Actually, the way I can think about it is that I can think of that, the top two-dimensional distribution, as a projection from an infinite dimensional thing to a two-dimensional thing. And this here is an infinite projection to an n-dimensional thing. So actually, I just have to think about the infinite dimensional object. That's the Gaussian process. And it's this property that allows us to talk about these infinite things, but never ever touch them. Right? We just know they exist, and everything we work on is a projection of that. So let's see the cool thing you can do with that. Okay, well, let's see the cool thing you can do with this. So let's take these two slices, red, green. We do exactly the same thing that we did before, and draw a two-dimensional sample. Cool? Got this? Well, actually, this two-dimensional distribution comes from a three-dimensional distribution. So I'm going to draw one in the middle. That's 3. Let's say that actually it's 5-dimensional. 5. Let's say it's 9-dimensional. 9. Let's say it's 17-dimensional. Ding. That looks quite nice, right? That actually looks like a function. It's not a function. It's 17 points connected by lines. But it looks like a function. And actually, I can keep sampling this to infinity. And if I could sample to infinity, you will kind of have a function, because you will know the value at every point. Right? Cool? So let's do that again, except for not with one sample, but let's do it with 10. So 2, 3, 5, 9, 17. That is just a sample, or 10 samples from a 17-dimensional Gaussian. Because I can always think about it as this infinite thing that I just project to different dimensions. And it looks like this. Kind of cool, right? That looks like functions. So if we then think about this infinite thing, rather than seeing these slices, we often look at it as this tube, right? It's this tube of variance around some mean function. So really, what we have is that somewhere up in the infinite space, there exists this infinitely long, infinitely big Gaussian distribution that we just decide to pick out stuff from. But the nice thing is that I know whatever I pick up is consistent with each other, right? So whatever projection I do, they're all consistent. So this is the way I think about Gaussian processes. It's just picking an axis-aligned projection matrix from infinity to n, and I get a Gaussian distribution, and all the clever math of Gaussians work. So, now then, that sounds great in some ways, but now you've led me to a parameterization of something which requires infinitely squared plus infinite number of parameters. This is really annoying, right? So we need to get around this thing somehow, right? Because I have to tell you what all these values are. There's a lot of them, right? So the way we do this, and this is what Rich talked a lot about, is that instead we parameterize the mean as a function of the location of the slice and the covariance as a function of two slices. If we parameterize those two functions with a certain number of finite set of parameters, I can compute this for any slice that you give me, right? And then I can do this, right? Cool? We happy about this? Does the analogy kind of follow? Cool? So, we parameterize the covariance as a function of its input. Okay? So K, so that variation in Y is parameterized by the location in X. Right? We're always parameterizing the Y value, but it's parameterized by the input. Right? And this is the useful thing, right? Because it requires me only to know the input to know something about the output functions. Right? The index set that this is the uncountable infinity. So if you go the real line, right, it's the uncountable infinity, and that makes it a process. This here is your, what I like to call, handle to input knowledge into the GP. The mean function as well, but we generally most talk about the covariance function, exactly as Rich said. This is the thing that gives us trouble most of the time. The mean function, if you know it, is just great. But the covariance function is what leads to all sorts of issues. Cool. So you can do things like smooth things, which is the stuff I've done so far, which just says the further you are away from the thing you're covariant with, the more you vary, you get smooth functions. We've seen samples like this, where I have a specific degree of smoothness. I can make that smoothness on a different length scale, and I get more varying things. Or I can make them on a really long length scale, and I get really smooth things. You can also do things like periodicity. Very easy, right? You say that over a certain range, the covariance grows, and then it stops growing, and you get something like this. Cool. Good. Do we have any questions on that? That was my introduction to GPs, and now I'm going to talk about stuff that Rich talked a little bit less about, but which is the thing that we do a lot. We have to add some data to these things now. If you believe me that this is a sensible measure, we now need to get the data into these things. Cool? No questions? Does that mean I'm doing a really good or a bad job? I'm not sure. Shoot, perfect.
Can you please explain a bit more this infinity? So how do we go from the finite index set and how we extrapolate it with the uncommon?
Yeah, it's the other way around. We never need to go to infinity, but we know that infinity, that the thing you're looking at is consistent with an infinite object, which means that if you're looking here and you're making some form of commitment of looking here, you're not making a decision of where else you can look, because you know that this thing here is consistent with everything else, which is really nice, right? Which effectively means you don't need to decide on the question you're going to ask at the time of setting up the model.
Yeah, so it is basically your assumptions.
Yeah.
But during the inference, it is you believe that your assumptions were true, so that the inference is right, so whatever the points you've seen in these indices you've chosen are like, they correlate with that.
Yeah, they do. Exactly. So you can compute the correlation with any other thing.
But how do you know that this finite index set is right?
You don't, right? Absolutely, you don't, right?
What are the ways to know if it's like, is it the right way?
I don't think one can think about that without taking up the application of it, right? So for example, you can think about very many things where I would reason about a specific domain, and I say, I look at this population, for example, and then someone who's a social scientist would say, that's great, look at this population here, but do not draw conclusions about that population from this, right? Because there's a rapid change here if you know, everyone who's retired or something, right? Like you can't translate from this to that, right? Now, the model will allow you to do that. If you've parameterized, say, age in this case, is your input is correct. But you shouldn't do that, right? Because it's a model mismatch, right? So this always have to come from external knowledge, right? Where you say it's actually a bounded thing within this. Yeah, good. Shoot.
If the external knowledge if there's a large variation, for example, if we are collecting data from the heart of every person and every data is different,
Yeah.
and the external knowledge is different, then how do we convince ourselves on the knowledge is different, then how do we convince that our choice is right?
Yeah, I think this is very, very hard, right? How does one, I think again, this is, you have to go to, how do you create trust for a model by a domain expert? And this is really interesting. There's very many different ways of doing this. Because I think different domains have a different knowledge, have a different narrative on how they believe. So actually, you took up hearts. I work a bit in cardiology, and I use these kind of models. And now we learn stuff and say, oh, cool, look at this. And then they look at it and say, what does this mean, right? What we found with them is if I generate data back to them and allow them a few twists and knobs, so they say, can you give me an age parameter? Okay, cool. So then they pull the age parameter around and they see what the ECG would look like, and they say, no. this doesn't happen. Like, it should happen like this. That's one way that I find work quite well, that they test the beliefs that they have and see if they test the things that they know, and therefore that builds trust for me, so they therefore dare to trust the things that I say about something that they don't know. But this is really, really hard, right? This is really, really tricky to do. But I think we always need to embed ourselves with the domains to get this right. All of this is about inputting knowledge, right? Like, this is the key thing, right? What knowledge can I take from a domain expert and input into a model? My argument is that these things are quite good. Because you see this relation thing that we built up, right? So for example, when I work with cardiologists, they would say, you know, these types of patients are generally quite similar. And I'm like, cool, covariance function, right? And I write that up, and then they say, you know what? In the winter, now I'm just guessing, right? In the winter in Sweden, where we looked at this, like, people's ECG goes like this. Periodic covariance, dunk, 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 right? Do-do-do, and then I build this up, do-do-do, and eventually I get something, right? Well, if they would start saying, parameterizing it, that's just really hard. What's the function of an ECG? I don't know. But the relative information, they sit with that, right? That's how doctors work. They'll be like, oh, I've seen a guy like that before. We better send him straight to the emergency, right? That's exactly how they function. So the relative way of extracting information is really useful. And that's why I like these things. Cool. Good, good. So, okay. So now comes the next fantastic thing, and I'm so running out. Well, I'll see. I got half an hour, right? Cool. We'll see if I'll make it. So, what we're going to do now is do inference, and we're going to do this, which is effectively, I've seen some output. I've dropped all the x's to make everything look prettier. So I just say, you've given me some outputs of a function at some location x. Now I want to say something about a function, values, at locations x star. So that's effectively f star. Cool? So this is the thing I want to do. I want the conditional distribution on the left. Cool? So the denominator there is the integral, which looks horrible. So what I'm effectively doing in this integration, if you take the right-hand side, that means I'm integrating over f star, which is take every possible function value at location x star according to how much you believe them and test them through the model. Okay, how many function values can exist across one line? Well, a Gaussian never goes down to zero, so it's infinitely many. So that is an infinite, I have to effectively take infinitely many evaluations. Then, when I've taken them, I need to check if they're consistent with the marginals that we've already connected. So I take every possible function. Cool, it goes through here, that's this function, and this function, and this function. And then I check every one that goes through the data points that I've seen. That feels like a horrible for loop to write. So effectively what I want to do is this. Here is my prior samples, and now I see a data point, and now I just want to write a for loop over this, and says for, you know, if going through this, keep, if not, don't keep. Right? You don't want to do that. That sounds horrible, but that's effectively what inference is. Now the cool thing is, you can do that in closed form. And it's trivial. So, let's see what we do. So, the joint distribution, f and f star, that we've defined, right? We said this thing, if you define the process over any subset, it's consistent with any other subset. So I can just write it over whatever subset I want. So the joint distribution is trivial to write down. The marginal distribution, the yellow one, is trivial to write down due to the marginal property. You just pick out the stuff you want from the joint. So you got that. Cool. Now, you know, through these things that Rich showed, that the thing in the middle there is a Gaussian or a Gaussian process. right? It's a Gaussian distribution through this linearity thing. So what I can actually do, this is exactly what Rich showed, I can just solve for that. Rather than doing this integration, I just do a bit of linear algebra and solve for this. I'll give you the derivation of it. It's quite tedious, but it's not hard. So you can just solve for this thing. So that's how you do it. You don't do the integration, you just do some linear algebra. And this is why Gaussian processes are really cool. So it effectively leads to this. You only need to define the joint Gaussian process, which we know looks like this, and then you can get the marginal by just picking things out, and if you solve for the conditional, it looks exactly like this. That's how it looks like. Cool. So to give a bit of intuition for what it does, I'm going to take these points here and say that I've observed these, and now I want to look what the distribution is at some other points. Okay? So let's take the first element. So the thing that is actually, if we go back here, that is the mean of the conditional distribution, the predictive distribution. So it's kx star x. So how does the points that I want to look at vary with the things that I have, times the inverse of how the points that I've seen vary with each other, times its function value. Okay? So that matrix there, what I'm showing there is this matrix. So what we can see here is effectively, this here is just a linear combination of the function values that I've seen, right? It's just linearly combined. These are just coefficients to the function values that I have. And what we can see is in the beginning, you have 0, blue here is 0. The first point, which is all the way out here, is basically going to be zeros times the function values that I've seen. Okay? Why is that? Well, because it goes back to the prior mean. It's so far away from the data, so I say it correlates very little with that, so it just gets the prior mean, which was 0. And then when you get into the data, you start getting values, and it starts interpolating these. If we look at the variance term instead, the way it looks like is that it's the prior covariance. This thing here is what the covariance would be of that slice of the Gaussian where I want to look at the data, minus, so corrected, by the information that I have in the data. So what it looks like is that the first term is the prior covariance. It says the points close to each other covary a lot. Then this term here is this thing there. If I subtract that, I get this. So I get variance far away from the data, little variance in between the data. But the cool thing is, if you look at here, this is just a linear predictor. It's just a linear combination of the data. That's it. Cool. So with that, you can then do things like this. Super simple. You just take that conditional Gaussian. That's like 3 lines of Python code to draw that, which is kind of cool. Another way of showing it is this, where you say, I plot the variance of one standard deviation, and I show it like, I hate these plots. These plots says a lot more. These plots don't tell you how the function varies. It could vary like this, right? Through this whole thing. And it would look exactly the same, right? So these plots I really don't like, and I'm going to show you an example right at the end for these. So if I can teach you one thing, show these. Show samples, don't show these. These are really, really misfortunate. And now the worst thing is, now small rant, people who do uncertainty in neural networks show these things. Look at the samples of a neural network. They will look bonkers, but these things look really pretty. So if you want to get a paper, show these. If you want to be a good scientist, show these. Good. So, okay, final intuition of this. So let's say now I have this function, and then I have this prior, and I'm going to show what the learning process is when we start seeing a data point after a data point after a data point. So the blue here is my prior. I now see one data point, zoop, see another data point, bonk, bonk, bonk. And this here is with a covariance function that just super simply says, if you're close to something that you've observed, you're probably quite similar. Smoothness, right? This here is just how this works, right? And eventually, I have very little uncertainty in this. Cool. So, now, that was kind of the things that I hoped to go through of just the GP introduction. Now I'm going to make a jump, so I'll check if there is any questions on this. It's kind of funny that I showed those bars after saying that I hated them, but, well, I'll get around to redo this plot. Cool. That was actually because this was from something else, but hey-ho. Cool. Okay, I want to do a leap of jump a little bit. So what I've shown you now, so far, is basically regression, where we've said, cool, we've specified a measure of goodness over a function. And then, as long as we can do this integration and integrate out our measure over functions, we can search for a solution that takes us from an x value to a y value. Nice. Now, let's say I instead have a problem where I don't know my input, right? So I have a solution. This is often called, it's a massive misnomer, but people call this unsupervised learning. To me, there's no such thing as unsupervised learning. If you have kids and tell them, go out and play unsupervised, they come back and have set fire to your car, and would you get disappointed? Yes. So, therefore, it was supervised learning, right? You had an opinion of how they played. Same thing, unsupervised learning, if you have some notion of what you want to get, it's therefore not unsupervised, right? Things are terrible misnomer. It should be called more supervised learning because you're actually not, you have less structure to it, so you need to provide more structure. Anyhow, that's this scenario. I now have output values, but I don't have any input values. And I don't know how the input values are connected to the output values. Now, we defined a measure on what we think good relationships between x and y is. Can we use that measure plus another measure that might say, I like these input structures, and see what we can do? So let's look at what this is. So, unsupervised learning, to me, looks like this. Think about an abacus. So you effectively have y values that can all, and your task is to give all the y values an x value, right? In one dimension. So you have these balls on an abacus, and your task is to position them. Now, as I said, we don't care about these data points. I care about what's between these data points. So I want to connect them with a function as well. So what I can do is this, right? One solution, perfectly happy about this. I can do this, another solution, perfectly happy about this. And I can do this, and I can keep doing this forever, right? They're all valid solutions. Now, come back to the flat Earth thing, right? We prefer certain of these solutions to other solutions. Now, what we have defined is a measure on these. What I can actually do is that I can take a solution like this. I've specified my GP prior, and my GP prior, I've specified what I believe good functions are. I can position the points in one set of x locations, and I can evaluate the probability of that function. In this case, the probability is really, really low. I can take this one, and now the probability is much, much higher. And I can take this one, and I think it's probably equally high as the former one, roughly, right? So actually, this measure over functions can also solve this thing, except for one thing. Say that I've specified a prior that loves smooth functions. How can I make this smoother? Yeah, I can move the data points as far apart as humanly possible, right? And it will be smoother, right? It will just be flatter and flatter and flatter and flatter. So if I add a prior that says, you know what, I want the range of x values to be something like this, you can chuck exactly this thing and learn an unsupervised learning structure. And I think Søren will talk a lot more about this, but this was my brief intro to this. So as long as you have this measure of this solution, you can use it for this as well. Right? Cool. So, in some ways, regression, there's an infinite number of possible functions that connect the data equally well. A GP provides a measure over these solutions that makes the problem well posed. In unsupervised learning, or whatever now we should call it, there's an infinite number of possible combinations of input and functions to generate the data equally well. A GP and a latent space prior, so a prior on something on X, provides a measure over these solutions to make the problem well posed. It's really just the same thing. Cool. So, now's the question. It's a bit of a tricky one. I'm a little bit over time, which is a bit bad. So, do people have questions? So we can either do 15 minutes of questions, or I can try and do some more stuff. Should I go ahead? Cool. So I'll go ahead with this. We'll see if we are allowed to run over a little bit. So now I've told you all the nice stuff. TPs are great, right? They're lovely. They do all sorts of nice things. All the computations are easy and all this stuff. This is how we lure people in. So you drink the Kool-Aid, and then you start a PhD, and then you realize, shit. There's all these things that they didn't tell me, that inverses are like cubic complexity, and there's like numerical instabilities, and there's all horribleness. So this is when we now take off our nice principled Bayesian hat, and we become realists. And that's when we get to approximate inference. So what we do a lot is integrating stuff. Integration is horrible. It's really hard. And we can think about this thing, for example, here, which is actually what I showed you before. Quiet. So let's just look at this integral. If f is a Gaussian process in this case, and let's say p of x is any distribution, right? Or let's say it's a Gaussian for that matter. So f here, p of f given x, is effectively, because it's a Gaussian process, it parameterizes effectively every possible function. Now, if I take the distribution p of x, which looks like this, and I push it through any function, right, what will the output look like? Well, it can look like anything, right? This means it's not something I can parameterize, right? Because I can't write up the parameterization of it. It's guaranteed to not be Gaussian, right? Well, if that's a linear function, that's it, right? Except for that, you're going to get something coming out on this side that I can't write down. And that means this is analytically intractable. You can't do these integrations. So we have to approximate. And the way we approximate these things is either doing MCMC, and I'm not going to talk about that. I'm going to talk about variational inference on this. And how many know about variational inference? We've got a few? Good? Okay. So I'm just going to give my hobby explanation of variational inference. So let's say what we have is that I want to get this object p of y here, right? P of y comes from an integration where I take p of y given x and I integrate out p of x through this. Now what I've said is pushing that distribution through this function leads me to something intractable. Okay? There's another way of writing p of y, and that is using Bayes' rule and writing as the likelihood times the prior divided by the posterior. That's the same thing, right? And I kind of said I don't like integration because it's hard, right? Now, in some ways, if I find the posterior distribution, well, now I can use this math to get this, right? I don't actually have to do the integral. So in some ways, if I want this, the evidence of the margin likelihood, if I have the posterior, I kind of have everything so I can get it anyway. So what we're going to try to do is that we are going to try to approximate the posterior distribution with something so that I don't have to compute this integral. So directly approximate the posterior. And the way we're going to do this is that these arrows here shows dependencies. So what I'm going to try and do is that I'm going to say, I'm going to come up with a distribution over x that I call q, which I want to approximate with this, and it has a set of parameters, theta, and I'm hoping that these parameters encapsulate all the information coming from y, so I can cut that dependency, right? So that distribution there doesn't need y, because that thing is the tricky one, right? So I'm going to hope that theta encapsulates all that information. Okay? So let's look at that. Let's try and write up a way of doing this. Let's try and go reasonably slow now. This is my only-ish slides with lots of math on. So I have this p of y. This is the object that I want. I'm going to look at logs, because it just makes everything easier. So I got log p of y. And then what I'm going to do, this looks completely not sensible at all, but I write up, I want to somehow involve the posterior distribution in this. So I just write this, right? This just integrates to 1 log of 1, so it's 0, right? So that thing itself, the thing I added, is just 0. So it doesn't add anything. Okay? Please stop me if there's confusions now. And then what I'm going to do is that I am going to do something quite... I'm going to take a q. Again, I'm integrating over x, and q is a distribution, so it integrates to 1, so it doesn't matter in this case. I'm just going to add this q term to both of these places. Okay? So now I've got all the objects that I want. So I've taken p of y, and I've written it as this confusing set of things. I got the q, I got p of y, and I got the posterior. Okay? So here, I've just merged them onto the same, put them all on the same form. That's why I have this q, so I can go into the logs in this way. And then, I'm just taking the denominator, which is just the joint distribution in this case, right? P of x given y times p of y is just the joint distribution. Okay? Now comes a big step. So what I've done now is that I've taken down the denominator. So let's look at the middle term. Taken down the denominator and split the denominator and denominator out like this. And then I've added, and you'll see in the next step why I've added this silly term. It's again something that is 0. I just need a few more q's to deal with. So I've just added this thing. Okay? Now I'm going to take one of the q's there and put that on the last term. Okay? Now this leads me to 3 different terms. Okay? I got one term, first blue term, only consists of q's. Okay? Q is something that I will parameterize. And then I have something that consists of the joint distribution and the q. The joint distribution is something that I know, right? If I don't know it, well, then you have other work to do. If you know your likelihood and your prior, you multiply them. Multiplication, hell of a lot easier than the integration. So you can do that. So you got this term. This term, however, is the thing that we don't know. Okay? This is the horrible term, because this is the term that contains the object that we don't know about, the posterior, the thing that we want. Okay? Do we follow? Nod heads or shake heads? Nod heads, I see, good. Nodding head is good. Okay? Then we're going to exploit something called the Jensen's inequality, which is just a very simple thing. So if I got this blue function here, terrible. If I got this blue function here, then if I take a linear function under that, if I take any of those values, it's always going to be below the blue one, right? So if I take any convex function, or concave in this case, if I now take, well, you can see it on the next slide. Oh, if I take any interpolation along the line, they're always going to be below that one, okay? And we're going to exploit that because the log has exactly this behavior. So let's take the term that we don't know. And what we'll do is that I'll first flip this around. So I'll change the numerator and denominator and get a minus sign out from the log. And then I'm going to do Jensen's inequality on the log. So what I do is that I move the q of x inside the log, right? So now I'm on the blue function, effectively. So that means this here, if I get q of x, those two cancels, which means this here is a lower bound, log p of x given y, log of the posterior, is a lower bound on this. And now, that's just the distribution over x that I integrate over x. So it's log of 1, 0. So that whole term is bounded from below by 0. So it's always a positive term, right? That's the thing we need to know. And then we need to know one more thing. Let's say that we assume that our q of x is exactly the thing that we're looking for. If this is true, well, now I plug this in, I get log of 1, so I get 0, right? So what we know from this term is that this thing here is called the Kullback-Leibler divergence. It's a measure of divergence between distributions. If it is 0, it's only ever 0 if the two distributions are equal, and it's always positive, right? So we know two things. It's 0, where I want it, where the thing, if the two terms are equal, and it's always positive. So what that means, if I plug this in here, the two terms that I think I can compute, I can just say that this whole thing, the two blue terms, is a lower bound on the left thing. And this here is called the evidence lower bound. Okay? And it's tight, which means it's 0. It's an equality if q of x is equal to this. So now I have a measure, an objective function, that says if you manage to make this shrink as much as you can, that term there, the red term there, how do you get it to shrink as much as possible? Well, the easiest way to look at it is this. So the two blue terms I'm calling L, and the red term is just this KL thing, and this here is what they add up to, right? If I want to make that KL term shrink as much as possible, I need to make this as big as possible, the blue terms. So now I can search for a Q distribution that maximizes the two blue terms. Okay, and that's what we often do with Gaussian processes. These are the things. It's a little bit tricky. Sadly don't have time for that. Overran quite a bit. I do exactly like Rich. I keep adding slides, and then I end up somewhere where I didn't intend to. But it's a little bit tricky. There's a little bit of trickery to do this on Gaussian processes, but most of the approximations that you see are going to use evidence lower bounds, are going to use variational inference to find them. And the way, just hand-wavily, how you do this is you make Q, the approximate distribution, a non-parametric distribution itself. And the intuition for thinking about that is that, say that I got 500,000 million data points here. Now, this thing, in a non-parametric thing, this curve doesn't have 500,000 million parameters. It doesn't have that many degrees of freedom. So what I do is that I pick a subset, and I say, these subpoints should represent this. And I represent the approximate distribution using only these, and now all the expensive math happens on these instead of all these. That's effectively how we do things. Very hand-wavily. Cool. So I'll jump through these and get to a better conclusion. That was just how we do it. I'll share the slides, and I'll be here for a few days, so we can talk about that later. I'm sure it will come up. Vincent might talk about things like this as well. Cool. So, just to summarize things, most important thing, there is no free lunch. Anything that learns something does so by being biased. Bias is a good thing for machine learning, for any learning. If you expect anything and believe anything to be true all the time, you're not going to progress particularly quickly. So what we want is models that are as biased as possible to the right thing, right? That's the hard thing, right? We want to include all the stuff that we know into something. And I think the biggest machine learning problem when you work on real-world problems is actually the domain experts, or cardiologists or other people, they know hell of a lot more about the data that we can't use. The biggest machine learning task is how we can develop models so their knowledge can be used. And I bet you in most cases then we'll solve everything by linear regression. Cool. And then the second thing, so now I put in this bias, this really strong bias about something, and then I got something out. The only way you can explain what you got out is in relation to what you put in. So if you don't know what you put in, you can't say anything about the output. And this you have to be really, really careful about. Noam Chomsky calls this the inductivist fallacy. When people say, oh, I threw this algorithm at something, and then you got something out, and then you come up with why it's done this. No, the why can only come from what you put in, right? Cool? My explanation of the flat Earth, right, or why we laughed about that explanation is just because we don't believe in that. Right? It explains the data perfectly, right? And I bet you so many models in this world are flat Earth models if the domain expert would actually go in and see the explanation that we had for them, right? And that's really scary. Cool thing, GPs gives you a little bit of a handle to do this, I think. So, maybe we don't need to do this here, but, you know, I started off talking about being Bayesian and how you think about things. I don't think anyone can have an argument about why we should mix knowledge and data. The question is just how you mix them. If you want to argue about being Bayesian or not, it boils down to if you believe in marginalization. And I think that's it. I tried to show that with this space notion of how you stretch and compress parameter spaces. That's how I think about it, and that makes sense to me. I don't want to be more religious about it than that, but I think that's what it boils down to. If summarizing things like this is the way to build up new measures, that we can have a discussion about. So I believe you can be pragmatically non-Bayesian, but it's very hard to be motivated from a philosophical angle. Cool. And maybe I should use yeah, I'll do this as well. So we talked about non-parametrics, and the notion here is that you move a relationship of measuring what you think about a function, so how you parameterize something, where you don't think about the parameter space directly, but you parameterize how data or instantiations that you've seen relate to each other. It's still a parametric problem, but this is how you think about it. I think this makes so much more sense. As soon as you get high-dimensional data, this is how we all reason. Like, think about how you should choose a restaurant this evening, right? You're not going to come with ingredients and like all these things. No, you're going to say, I went there, it was really nice, it had this thing. Oh, but what do you think about that? And then you relate things. Oh, that one was better than this. Cool, it's non-parametric. We reason about this all the time, right? So if you then build models of non-parametric parameterization, it leads to different kinds of stochastic processes. If you start putting distributions over these things, because they have an infinite capacity, it becomes stochastic processes. And we've seen the Gaussian process in this case, but there's others as well, right? And Kolmogorov has this beautiful theorem of the characters of a distribution that allows us to think about an infinite realization of this. Cool. Now, I'm going to stop there. I had a few more things. Oh yeah, let me just do this. This is just the last thing, because now I'm going to justify my rant about these plots. Cool. So people do deep learning, right? It should be called composite function modeling, because that's what they do. So let's take this function here. Now, if you show things like this, This is a composite Gaussian process, actually. It looks like this, right? It looks beautiful. That's why I hate these plots. Well, I'll show you samples from this function. How do you think functions looks here? You can't say that. The only thing you know is that it looks like, you know, one way of thinking about it is varies nicely and then it sharpens and then it varies nicely. That's how samples look like. The only thing it is, it's a model that says you can either be -1 or 1, and there's a biased coin toss, and here it's more biased to being -1, and there it's more biased to being 1, but it's jumped between 1 and -1 the whole time. That's how they look like, and that's why we should never, I'm going to change my slides, we should never do these plots. Please do these plots, because this is what tells you what functions you've learned. This just tells you something else. Right? It's a much more, if you want to think about it mathematically, this here is plotting the diagonal of the covariance matrix. This is plotting the whole matrix. And it's a very different thing. Cool. And with that, I'm going to stop. Cool. Thank you very much. Sorry for running over.